Welcome to this deep dive for the love of physics. We are Mr. Jager's assistant, and we want to give a massive hello to all you amazing students at Ishik Boys High School.
Yeah, especially everyone in Mr. Jager's physics class. Great to have you listening.
Definitely. So today we're going to unpack something you see, well, pretty much constantly, probably without even thinking much about it. We're looking at how light behaves when it hits stuff. Specifically, reflection of light. And we'll zoom in on flat mirrors.
It's a good one.
Yeah. Our mission, basically, is to take these ideas, which maybe sound a bit tricky, and make them super clear, really relatable.
Just like you're learning in class.
Exactly. Get ready to see things, literally, in a new way.
It's pretty amazing when you think about it, isn't it? Reflection is just so basic to how we see anything.
Totally.
I mean, that first look in the mirror when you wake up, seeing your friends, even just how your phone screen lights up, it's all about light bouncing around.
It really is fundamental.
Absolutely. It
Wow.
shapes our whole visual world.
Okay, so let's start with the basics. Light, generally speaking, just wants to go straight, right?
Yeah. Through something consistent, like air or water, it just beams along in a straight line. Pretty straightforward, no pun intended.
Right. But then, what happens when that light beam, cruising along, suddenly hits something different? Like it runs into a wall, or maybe a shiny mirror.
Ah, that's where the action is. Its path has to change.
Exactly. That sudden change where the light kind of bounces off the surface of this new thing, that's what we call reflection.
Think of it like a super obedient pool ball hitting the cushion and bouncing off perfectly.
Nice analogy. You know, like in the book, that example of using two mirrors to try and see the back of your own head after a haircut?
Oh yeah, that classic setup.
It seems impossible, but it shows reflection doing its thing, bending the light path so you can see around corners, basically.
But, you know, it brings up a good point. Does all the light bounce back? Does it always reflect perfectly?
Oh, good question. No, actually.
Right. When light hits something new, some of it doesn't bounce back. It actually gets absorbed by the material.
Yeah, it's soaked up.
Especially if the surface is dark, or maybe not very shiny, like a dark wooden table. Lots of the light hitting it just gets absorbed as heat, doesn't bounce back to your eye.
That's super important to remember. And it's not just dark stuff. Even really good mirrors, like the ones we use every day, they aren't perfect.
Nope, not 100%.
They might reflect maybe, 90% of the light? Something like that. But never all of it.
Exactly.
Like if you look at that picture, figure 14:5, with the golf ball between two mirrors, you see lots of reflections, right?
Fainter and fainter.
Right. They get dimmer the deeper you look.
Yeah.
And that's because each time the light bounces, a little bit gets lost, absorbed by the mirror surface.
So less light makes it to the next image. It's a real effect.
Definitely shows that reflection isn't always total. Okay, so light bounces.
Yeah.
But does it always bounce the same way?
No. It really depends on the surface it hits. Is it smooth? Is it rough? That makes a huge difference.
Okay, so let's talk rough surfaces first. What happens there?
Right. So when light hits something bumpy or textured, think like a piece of paper, your t-shirt, maybe some unpolished wood.
Got it. Rough stuff.
The light rays hitting it get scattered. They bounce off in all sorts of different directions. This is called diffuse reflection. Your book shows it in figure 14.6a. The rays are going everywhere.
Ah, okay. And that scattering, that's actually useful, right?
Totally. It's why you can read the words on that piece of paper from pretty much any angle.
Because the light's bouncing off in all directions, so some of it's bound to reach your eyes wherever you are.
Exactly. Same reason you can see your friends, not shiny clothes from across the room. Diffuse reflection.
Okay, so that's rough surfaces. What about the smooth ones? Like mirrors?
Right, the opposite happens there. That's specular reflection. This is for your really smooth, shiny surfaces. Mirrors, obviously. Or like, a super calm lake surface.
The water, yeah.
Yeah. On these surfaces, the light reflects in a very orderly way. All the rays bounce off in basically one single direction. Figure 14.6b shows this nice, neat pattern.
And when we say smooth in physics, we mean really smooth, right? Like atomically smooth almost.
Well, maybe not quite atomic, but yeah, the bumps and variations on the surface have to be tiny, much smaller than the wavelength of the light itself.
Okay, that makes sense. Needs to be super flat for the light waves.
And this is why you get a clear, sharp image in a mirror. Or see that perfect reflection on the still pond. All the light rays bounce off together, preserving the image information.
Gotcha. So for the rest of our chat today, when we say reflection, we're mostly going to be talking about this type, right? Specular.
Yeah, let's focus on specular reflection. That's where the really interesting rules come in.
Okay, cool. So specular reflection, smooth surfaces. you said there are rules, like
Okay.
it's predictable.
Oh yeah, very predictable. There's a really simple but powerful rule called the law of reflection.
Okay, law of reflection. Sounds important. How does it work?
So, first, imagine the light ray hitting the mirror. Right at that point where it hits, you need a reference line.
A reference.
Yeah, draw an imaginary line straight out from the mirror surface, exactly perpendicular, like at a 90-degree angle to the mirror at that point. We call this line the normal.
The normal, okay,
Yeah.
perpendicular to the surface. Got it.
Now, we measure angles relative to this normal line.
Oh, okay.
The angle between the incoming light ray and the normal, that's called the angle of incidence. We usually use the Greek letter theta for that.
Angle of incidence.
What?
Incoming ray to the normal. Makes sense.
And then the angle between the reflected, the bouncing off ray, and that same normal line, that's the angle of reflection. And we often call that theta prime.
Angle of reflection. Reflected ray to the normal. Okay, got the angles. So what's the law?
This is the beautiful part. The law of reflection is simply the angle of incidence equals the angle of reflection.
Wait, that's it?
That's it, shall I? Whatever angle the light comes in at relative to the normal, it leaves at exactly the same angle on the other side of the normal.
Wow. So if it comes in at, say, 30 degrees to the normal,
It bounces off at exactly 30 degrees to the normal. Perfect symmetry.
that is simple and elegant. And you can kind of see this in action, right? Like in figure 14-7a.
Absolutely. It shows if the incoming rays are shallow, close to the mirror surface, the reflected ones are shallow too.
And if they come in steeper from higher up.
The reflected rays go out higher up as well. It just follows that angle in equals angle out rule perfectly.
Cool. Okay, so we've got light, reflection, smooth versus rough, and this law of reflection.
Yeah.
Let's talk mirrors, specifically flat ones, the kind most people have at home.
Right. The simplest type of mirror, but they still do some pretty interesting things with light.
Yeah, like how they make images appear. When light from an object, maybe like your pen, bounces off the pen, hits the flat mirror, and then reflects to your eye.
Yeah.
It doesn't look like the light came from the pen directly, does it?
No, it looks like the light is coming from behind the mirror. Your brain traces those reflected rays back.
Exactly. And that thing you see behind the mirror, that image of the pen, that's what we call a virtual image.
Virtual, yeah. Key word there.
Why virtual? What does that mean?
It means the image appears to be there, where the light rays seem to converge if you trace them backwards behind the mirror. But the actual light rays, they never go behind the mirror. They bounce off the front surface.
Ah, so the light isn't actually coming from that spot behind the mirror. It just looks like it is.
Precisely. It's an optical illusion formed by where your brain thinks the diverging reflected rays originated.
So you couldn't, like, put a piece of paper behind the mirror and see the image projected onto it.
Nope. Doesn't work that way. Because the light doesn't actually focus there. It only exists for the viewer looking into the mirror. Like a little light ghost.
A light ghost. I like that. Okay, so these virtual images in flat mirrors, they have specific characteristics, right? Things that are always true about them.
They do. Couple of key things. First, the distance.
Okay.
The distance from the actual object to the front of the mirror, let's call that the object distance, PM.
P.
Okay, is exactly equal to the distance from the mirror to where the virtual image appears to be behind the mirror. That's the image distance, Q.
So P, object distance equals image distance.
Yeah.
Always.
For a flat mirror, yes.
Always.
If you stand 1 meter in front of a mirror.
My reflection looks like it's 1 meter behind the mirror.
Exactly. Which means it looks like it's 2 meters away from you. 1 meter to the mirror, 1 meter behind it.
Ah, right. That makes sense why reflections seem further away.
Mhm.
Okay, what else? Size.
Size is simple. The image height, let's call it h, is exactly the same as the object height, h.
So H. The reflection is the same size as the real thing. Not magnified, not shrunk.
Correct. Flat mirrors don't change the size.
Okay, distance is the same, size is the same. What about orientation? Things look kind of flipped, right?
Ah, yes. The famous mirror reversal. It's specifically a right-to-left reversal.
Right to left, so not upside down.
Nope, not up and down. If you raise your right hand, your reflection raises what looks like its left hand.
Yeah, I've seen that. Like the example with the watch in figure 14-9. The numbers are backward. The hands seem to sweep the wrong way.
Exactly. It flips front to back, which our brain interprets as a left-right swap when we look at our reflection facing us.
Fascinating. Okay, so virtual, same distance, same size, but left-right reversed.
That's the summary for flat mirrors. And, physicists have a way to actually figure out where these images form, especially if the setup gets more complex than just one flat mirror.
Oh, yeah. How?
They use something called ray diagrams. It's basically a drawing technique.
Like sketching it out?
Kind of. You draw the mirror, the object, and then you carefully draw a few key light rays, leaving the object and hitting the mirror.
And then you use the law of reflection. Angle in equals angle out.
Exactly. For each ray, you apply the law to see where it reflects. Then, the clever part, you extend those reflected rays backwards behind the mirror using dotted lines.
Ah, tracing them back to where they seem to come from.
Right. And where those dotted lines intersect behind the mirror, that's where your virtual image is located. It's a visual way to calculate the image position and characteristics using geometry.
Cool.
Yeah.
So you don't always need complex math. You can visualize it.
It's a really powerful conceptual tool, yeah.
Awesome. Wow. Okay. That was quite the journey through reflection.
We covered a lot of ground.
Yeah, we really did. So just to recap, we talked about what reflection even is, that bounce of light. Then the big difference between diffuse reflection from rough surfaces scattering light everywhere,
Which lets you read your book.
and specular reflection from smooth surfaces like mirrors where light bounces predictably.
Following that simple rule.
The law of reflection. Angle of incidence equals angle of reflection.
Yeah.
And finally, we looked at flat mirrors, how they create those virtual images.
The light ghosts.
Haha, light ghosts. That seem to be behind the mirror, same distance, same size, but with that weird right-to-left flip.
You got it.
Okay, so thinking about all that, here's something for you listeners to chew on.
A reflection question.
Exactly. Why do you think the rear-view mirror in a car works so well for seeing behind you? But if you just took a piece of aluminum foil and crinkled it up, even though it's shiny, why wouldn't that work as a good mirror?
Ooh, good one. Think about smooth versus rough surfaces.
Definitely something to ponder.
Yeah.
Thanks so much for joining us on this deep dive into the physics of light.
It was fun.
Stay in contact with your physics teacher, stay creative,